So we're looking at section 12C, which is entitled apportionment. Apportionment is basically a fancy way of trying to divide up people or objects among various groups or individuals. An example that I'll try to give you here is, let's say, for example, Lowe's Home Improvement, and let's just small scale, let's talk about just North Carolina. Let's say central headquarters of Lowe's Home Improvement in North Carolina receive a large shipment of snow shovels, and we'll pretend, okay, hey, it's wintertime. And as you might imagine, those in the stores in the mountain region would obviously have more of a need for those snow shovels than we would here on the coast. So what Lowe's may be interested in doing then is, okay, well, let's divide up our stores between the coast, the Piedmont, and the mountains, and then look to see from last year's sales how many were sold in each of those regions. And then they would quickly find out that most likely more were sold in the mountains and Piedmont versus the coast. And what these methods of apportionment that we're going to look at today is to seek to show you how, with that Lowe's example, that since the mountains and the Piedmont likely have more of a need, they're going to be allocated more snow shovels than we would here on the coast, but it would be done as fairly as possible. Okay, there's a lot of history behind apportionment. I gave you a brief synopsis here in the notes, but there's quite a bit more in your textbook, so I'm going to let you take a look at that. Okay. There are 4 basic methods of apportionment. We are just going to focus on the first 2, Hamilton's and Jefferson's method, but Webster's and the Hill-Huntington method also exist because, as we'll talk about, there are some flaws with Hamilton and Jefferson's method. Okay. Hamilton's method, we'll start with that one first. So I've got it sort of designed that I'll do one and then let you try the next example in the notes, and then I'll show you Jefferson's method and do one together and then let you try one in the notes. And then there's also a practice in Blackboard for this section. You're likely going to need to try that practice just to get yourself feeling better about it. The formulas for standard divisor and standard quota I know are on your formula sheet. So standard divisor is just the total population that you're looking at divided by the number of items to be allocated. So like for my Lowe's example, it would be the total number of stores that they have divided by the number of snow shovels that they had received. And then I'm going to take that standard quota and look at the population for a particular store and divide it by that standard divisor that we had previously. So again, I'm going to give you a concrete example here on the next page. I'll put all of this down. You'll round your standard quotas down to the nearest integer. Initially, then, each group is going to receive its lowest quota. And then you're going to distribute leftovers to the largest fractional parts, okay, until everything has been distributed. So let's flip on over so you can see what I'm talking about. So here in example 1, let's use Hamilton's method to solve the U.S. House of Representatives delegate apportionment problem. But we're just going to look at it in terms of 4 states. Of course, we know, U.S. has 50 states, but we're just going to, that'd be a large table. So we're just going to look at 4 states, and let's just assume that those 4 states want to create a legislature, that has 100 seats. So the population of each state here is then noted. So we're saying State A has 936 people, State B a little over 2,700 people, State C and State D. Adding all of those up, then we're looking at a total population then of 10,000 people. Standard. The very first thing we want to come down then is we want to find the standard divisor. The standard divisor is equal to the total population. So in our case, like we just found, is our 10,000 divided by the number of items to be allocated here. And so what we're having to allocate is these 100 legislative seats. So 10,000 divided by 100, divide that out, and you're going to have 100. That is my standard divisor. So then the next step is to find the standard quota for each particular state. So the standard quota is the population for each particular group. So here it's the population of each state divided by my standard divisor. So dividing by my 100 that I just found there. That standard divisor is going to change on every problem. So here, my standard quota then would be to take that 936 and divide it by 100. And so, of course, that's going to give me 9.36. Likewise, I'm going to take state B, 2726 divided by 100. Of course, that's going to give me 27.26. All right, so the next one is just to save myself some room. 2603 divided by 100, so that's going to give me 26.03. Likewise, 3735 divided by 100, 37.35. That last column, the total, means nothing, so you do nothing there. Then, as you saw in the directions that said for the minimum quota, your minimum quota is to take each of these standard quotas and round them down. So that 9.36, essentially, I'm just ignoring the decimal part. Minimum quota then for State A is going to get 9 delegates. State B is going to get 27 delegates. State C, 26. State D, 37. Add this row all the way across, and you should find that that would add up to 99. So what that means is, at this point, I have allocated 99 of those seats. I still have 1 seat left over because I'm trying to give out these 100 seats. And here's where we're trying to figure out, where does that extra seat then go to? According to Hamilton's method, he says, well, it goes to the one that has the highest fractional remainder. And the fractional remainder is going back and looking at all of those decimals from the standard quota. So I gave you a line in your table here to actually write down what the fractional remainders are. So for State A, it would be 0.36, State B, 0.26, State C, 0.03, and 0.35. And again, this is another case where the total column doesn't have any bearing. Then, like I said, according to Hamilton's method, looking at this row now, whichever number is the highest is where I get where that extra seat goes to. So as you can see then, 0.36 is the largest. That's where my extra seat then is going to go. And so then that one is going to change from 9 seats to 10 seats. Everybody else is going to stay the same. I add across and I get 100. Okay, say for example when we had added across here and we had gotten 98 and you said, oh, I've got 2 seats left to allocate. What I would look then is in this row, the highest remainders, 36 and 35, they would each get 1 additional seat like that. Okay. So that you wouldn't give both of those seats. What I'm trying to say is you wouldn't give both of those seats to Set A. You would then start doing it one at a time like that. Okay. I definitely now encourage you to go down and look at example 2 and try Hamilton's method from top to bottom. Okay. I'm going to flip on over then and look at Jefferson's method. And we go to Jefferson's method because, like I had mentioned before, there are some problems with Hamilton's method. And namely, they're referred to in your book as the Alabama paradox, population paradox, new states paradox. I'll let you look a little bit more specifically about what those paradoxes mean. It's not a huge concern in the class, but history-wise, if you're wondering, well, if you've got Hamilton's method, what's wrong? Why don't we just go with it? There are some issues that came up with that. So then historically they moved into using Jefferson's method. He said there's got to be a better way for distributing those leftovers. So in comes Jefferson's method. So you still find your standard divisor, your standard quotas, and minimum quotas like you did in Hamilton's method. So it's very similar. If there aren't any extra seats left over after you've done that minimum quota, your apportionment's complete. However, if you do have some leftovers, then this is where Jefferson's method becomes a little bit more involved. You choose what's called a modified divisor, and generally it will always be lower than your standard divisor. Use it to compute modified quotas by dividing each state population by the modified divisor. You're again always rounding down. You're going to continue to use that modified until you have gotten everything apportioned out. If if again, after you've done that modified quota and you have leftovers, then you've got to find another modified divisor. Just know for testing purposes, whenever it comes to finding that modified quota, as you can see down in example 3, I have given you what those divisors are. I would not expect you to have to come up with that, because it does involve quite a bit of trial and error if you start trying to do that by hand and stuff like that. And we don't want you to be concerned about that when you're taking a test, okay? So we would tell you, okay, use this modified divisor, okay? So what I did is I looked at the House of Representative problem that we just got finished doing, where we still wanted those 4 states to get 100 seats. We wanted to compare now. Well, you saw how Hamilton's method gave a particular apportionment. Well, what would happen if we did Jefferson's method? Well, here's the reason why we were going to use Jefferson's method, because after you had done, your standard, we had found our standard divisor of the 100, taken each of these populations and dividing it by 100, I still got this. But once I added across and I still had a seat left over, I can't stop there. Remember, Jefferson does not base anything on these remainders. He then goes to a new lower modified divisor. So he says, okay, take each of these state populations now and divide them by 99. So I'm going to take 936 and divide it by 99, and that's going to give me 9.45. Again, I'm taking each of these populations and dividing by 99. So, sorry, that doesn't look 99. The next one, 2726 divided by 99. After you divide there by 99, you should get 27.54. 2603 divided by 99 should give you 26.29. And 3735 divided by 99 should give you 37.72. Round down, so just taking the whole numbers, 9, 27, 26, 37. As you can see, after you add those across, you still have 99 seats. Since I haven't allocated all 100 seats, I haven't picked the best divisor, so I go down. So now let me use 98. So now I'm going to take each state population again and divide by 98. So I'll take 936 divided by 98, and that's going to give me 9.55. 2726 divided by 98, that's going to give me 27.82. The 2603 divided by 98 will give me 26.56. And then lastly, the 3735 divided by 98 will give me 38.11. Minimum quota, so rounding down, just looking at your whole numbers, 9, 27, 26, 38. Now if you add those across, all 100 seats have been allocated. And so if you notice, with Hamilton's method, when we did this example the first time, he gave the leftover seat to state A, and now here looking at Jefferson's method, he ends up giving the leftover seat to state D. So just like I mentioned before, Hamilton had several paradoxes that arose from his method. The paradox that's arising here from Jefferson's method is that he is allocating the extra seat to a large state at the expense of a smaller state, which is another issue. So I encourage you to try the next example so that you can get more familiar with that. And as you can see here in the next example, I've given you your modified divisors to try. Okay. And then lastly, as I mentioned at the top of the notes, there are other methods. It's the Webster method and the Hill-Huntington method. They also violate quota criterions, but they do it less often, which makes them a little fairer. Ultimately, though, there's no apportionment system that will be fair in all situations. So it's just a matter of trying to go with what's the most fair at the given time.